Oi, introducing inside out of distribution. Kind of a weird paper today, getting very into the theory of what it means to be out of distribution in different scenarios. I think it's a good thing to be thinking about, even if you're not going to do research on the specific paper area, whatever. It's a cool thought to have in the back of your head in terms of the really foundational basics of what is happening in machine learning. Before we get started, like, subscribe, comment, all the YouTube things, support with that YouTube join button down below or on Patreon or Substack. If you do through YouTube, that'll get you early access to these videos, and through any of them, you will get a unique Discord role. Join the Discord to discuss, follow on Twitter, and connect on LinkedIn. And of course, my obligatory disclaimer. Today, I'm going to call this a 1 or a 2 star. Let's get to it. So intuitively, out of distribution OOD refers to data instances that significantly deviate from the training data distribution. And this definition should be carefully distinguished from concept drift, which describes changes in a data's underlying distribution over time. So the first is a data collection problem. The second is a problem of the real world and the thing in it that generates data is actually fundamentally changing. And the insight of this paper is that one can consider a binary separation between two types of OOD data, inside and outside of the training data. Here is a display of these concepts. In the case of one dimension here on the left, we see green is our sampled data. Inside OOD would refer to there being just gaps in the values of our actual sampled data in between. Outside OOD would refer to data that is literally outside the range of our sampled data. And you see it here again for a two-dimensional case. And in this case, notice that it can be a given data point can be inside along one dimension and outside along the other dimension, or outside on both and inside on both. And here is it for some high dimensional, aka some full-on image data. Now, how do we actually integrate this into the mathematical definition of OOD, right? Well, first off, there just are multiple definitions for OOD in terms of its math. Three well-adopted ones are Mahalanobis, I don't know how to pronounce that, distance, random feature z-score, and a Kullback-Leibler divergence metric. The first one, let's call it Maha, distance is just an extension of the second one, the z-score metric, for an n-dimensional case, so consider the same thing almost. Formally, if we have a probability distribution over n dimensions, characterized by its mean vector and a positive definite covariance matrix S, then the Maha distance from a given point to that probability distribution, aka the degree to which that given point is out of said distribution, is just defined as the point subtracted by the mean vector transposed times the inverse of the covariance matrix times, once again, the point subtracted by the mean vector. And that one matrix inside another matrix on either side should look familiar, and then just square root all of that. In contrast, another metric, the second one, a random feature z-score. Well, I should say that this Maha metric is basically just z-score across all dimensions. In contrast, the one that's proposed second, a random feature z-score, instead of doing across all dimensions, selects at random one specific feature and determines whether it's inside or out of distribution based on the said z-score given some threshold. Now, what they're going to establish here in this paper is a new metric that aims to capture the performance of a data-driven model on the different possible OOD configurations, aka inside versus outside, for a given problem. They're going to look at an n+1 dimensional regression task, where that final dimension, the +1, is the target feature, and we assume an OOD predictor, O, which accepts as input an actual function of the data and a new sample, and returns whether this sample is OOD with respect to the function or not. And we define this idea of inside OOD in a given dimension, the ith dimension, with respect to a data set, where a requirement of the definition is first that it is in fact qualified as OOD by the aforementioned assumed OOD predictor, and more importantly, the interesting piece here, it is inside if there exists two data points within said function such that our sample of interest x is between those two data points. And it's said to be outside OOD if there does not exist 2 points in the function such that x is inside them, aka it is outside, right? It's just the opposite definition, but again, still OOD by our previously assumed OOD predictor. However, these definitions are kind of weird. They're extremely sensitive to outliers. For example, if you had a data set with 1,000 samples, 999 and 999 of them, like all but one, being in a range between 0 and 1, while one sample is some very large value, then by that logic, a sample with a value of, say, 10 would be considered inside OOD simply because of that one outlier sample of the original data set. However, this is clearly not the behavior we would want from an actual definition of inside OOD, aka this prior said definition, is kind of messed up. And what this does is it requires you to divide the data set up and look at intersections of said data set and then compare a given sample X not to any point in the original data set, but instead to points in said divisions of said data set, which is a more robust definition, but also way more computationally extensive if you actually wanted to calculate it, because then you would have to make every single possible arbitrary split up of the original data set and calculate your definition according to all those possible combinations of arbitrary splits. But I mean, hey, now it makes a bit of sense. I'm going to spare you most of the details of the paper. Most of the actual stuff, it wasn't crazy interesting. I think there's just might be some implications down the line for the split up of inside versus outside OOD and how they affect things. But the experiments themselves, I wasn't too into them. Just a few more highlights to go. Interestingly, outside OOD configurations consistently lead to higher normalized root mean squared error compared to inside OOD configurations. So that might be an easier way to detect the outside ones at least. And an implication of this paper is that in terms of data augmentation techniques, it might be smart to purposely think about simulating both inside and outside OOD conditions, rather than just usually, I think people would usually do outside. And keep in mind the definitions of the paper today were defined in terms of regression. Those definitions, I believe, would not carry over easily to classification tasks. Now, I asked the question in my notes here, how would we intuitively define inside OOD versus outside OOD in the context of NLP? Just spitballing here, my first guess would be that if you look at natural language processing, LLMs and stuff, and their in-context learning and the tasks they actually have learned, a recent in-context learning paper that I had read found that these models seem to learn many different tasks and that they are capable of arbitrarily combining said tasks in the actual context prompt scenario, right? Meanwhile, if you ask them to do a task they have not seen before, not learned, not grokked, or at least, right? They just can't do them, and they obviously cannot combine an unlearned task with a learned task, right? I would almost define inside OOD, I'm tempted to anyways, I think I'm wrong, but I'm tempted to, as just unseen combinations of tasks, given that every task learned, assuming you break tasks down to the most fundamental basic building blocks of tasks, every task learned is more of a categorical issue than a regression type issue, right? I would say any task not seen during training, or at least not grokked during training, would be outside OOD, whereas there are probably a lot of fundamental ground block tasks, but most things done in language data are probably combinations of tasks, and that inside OOD would probably be something along the lines of an unseen combination of tasks. Hence why we were also impressed with in-context learning with LLMs and their abilities in that sense. Because I don't see how you would define inside OOD at the level of the most fundamental building block, like miniature tasks, right? But it makes more sense to me to say, oh, unseen combinations of tasks are inside in the sense that you have seen each of those individual tasks, but this specific combination itself was not seen before. So I would say that LLM's language, it might even, I'm just guessing here, be easier to cover and learn inside OOD scenarios than it is outside OOD scenarios. But yeah, that's the thoughts I had for today. Bit of a weird one, I guess, not up my usual alley. I'm definitely not an outlier detection researcher or anything like that. But let me know if you enjoyed this one. Like, subscribe, comment, all the YouTube things. Follow on Twitter and connect on LinkedIn. If you are a big fan and you want to support me, you can do so with that YouTube join button down below for as low as $1 per month, maybe 3, 5, or $10 if you are feeling very generous. That gets you access to these videos early before everyone else sees them. Also gets you a unique Discord role. You can also support through Patreon or Substack if you prefer. Those get you the Discord role, but not the unique or not the early videos. And with that, end of video.